Good day, everyone. I hope you are doing well. So, today we'll have a new lesson, and it's about nuclear chemistry. So, as we all know, chemistry is the study of the structure and behavior of matter, and most of our understanding of such phenomena comes from studying the gain, loss, and sharing of electrons. However, the nuclei the nuclei of some atoms can undergo change, meaning the protons and the neutrons in the nucleus can undergo change or transformation. So in this chapter, we'll explore more on that and turn our attention towards the center of the atom to learn what is meant by nuclear stability and to understand the various kinds of nuclear reactions. So basically, there are two forces that act upon the particles within the uh, uh, within uh, with, within the nucleus to produce the nuclear structure. So one is the strong nuclear force, and this is what keeps our nucleus together, meaning this nuclear force, strong nuclear force, holds the protons and the neutrons, collectively called the nucleons, together. The second one is the electrostatic force, and this is a this is a weak force, and this causes the opposite electrical charges to attract each other and like charges to repel each other. So this is a weak force, and this facilitates nucleus decay or the nuclear reaction. So this nuclear reaction causes transmutation, meaning the atom will change from one element to another and gives certain level of radiation. Radioactivity was first discovered by Henry Becquerel when he noticed bright spots in photographic plates when exposed to uranium mineral. So later on, he was awarded the Nobel Prize in Physics for his uh, discovery of radioactivity. So nuclear chemistry has many useful applications like the electricity from the nuclear power plant, in medical diagnosis like the magnetic resonance imaging or the PET scan. So this is a very interesting field. So let's have a quick review first on uh, the description of our nucleus. So our atom in general. So the atom is actually identified with two numbers. So there is atomic number, the Z, and then the mass number, the A. So when we say the atomic number, this refers to the number of protons in the nucleus, and the mass number refers to the number of protons and the neutrons in the nucleus. So we have this symbol of the element. So the A, that is written in the upper left side, and then the mass number, the Z, is lower left, and X is the symbol of the element. So some symbols here for the proton, that's basically the symbol of the hydrogen. So the symbol 1 1. So hydrogen is the only element or atom. The simple hydrogen is the only element or atom that has a single proton and no neutron. The rest, it has protons and neutrons. Okay, so for the simple hydrogen, the atomic number is 1, and the mass number is also 1. For the neutron, so the mass number is 1, and then the atomic number is 0. Electron, the atomic the atomic number is -1. So this is how we represent some of these particles, no, in the nucleus or in the atom, the atomic subparticles. And then also the positron, we also have this particle, but the symbol is it's just like it's an electron, but the charge is positive. So the Z, that is +1, is represented by the symbol beta, just like the electron. And then the alpha particle is just the helium atom. So these are the most common particles that we can see in our atom, and we'll cover in this topic. So it's important to follow the nuclear reaction. So there are some rules that we follow in looking at the in writing the nuclear reaction. So first, this when you balance the nuclear reaction, so the mass number is conserved, meaning the sum of the protons plus neutrons in the products must equal to the sum of protons plus neutrons in the reactants. So if you look at here, so in the reactant, the uranium reacts with a neutron. So the atomic number, so this is the number of protons here, 92 on the left. So on the right, the product side, so it should total to 92 as well. So 55, 37, that's 92. As well as the sum of protons and neutrons. So 35 plus 1, that's 236. And on the right side, 138 plus 96 plus 2 neutrons, that's also 296. Again, and also, of course, the atomic number or the nuclear charge must also be balanced. Okay. So for example, in this sample problem, the 212 polonium decays by alpha emission. So write the balanced nuclear equation for the decay of 212 polonium. So you write first the polonium, so the formula, no? So 212 polonium, and then you check in the periodic table the atomic number, so it's 84. So it emits an alpha particle or an helium, so that's one of the products. So you will determine what is the other element that is formed from polonium. So the mass number must be 212, so the total must be 212, so the A must be 208. And for the atomic number, the Z, so the total must be 84, so 84 minus 2, so the atomic number of this X is 82. And you find it, next is you find what element is that in the periodic table, and the 82 is actually lead. So this is now the complete balanced nuclear equation. When your polonium 212 decays and giving you the alpha particle. So basically, this is the comparison between the usual chemical reactions which involve electrons. So electrons, and then our nuclear reactions which involves the proton and then the neutrons. So for the usual common chemical reactions, atoms are rearranged by the breaking and forming of chemical bonds. But in the nuclear reaction, so in other words, there's no new element that is formed. In the nuclear reactions, elements or isotopes of the same element are converted from one to another. So in nuclear reaction, there is a transmutation, meaning the transformation from one element to another. But for the common chemical reaction, there's no change. There's no transmutation. So you still have the same kind of atoms because only electrons are involved. So only electrons in atomic or molecular orbitals are involved in the breaking and forming of the bonds. But in the nuclear reactions, not just the electrons, but also the protons, the neutrons, these particles are involved in the process. Reactions are accompanied by an absorption or release of relatively small amounts of energy. That's for chemical reactions, but for nuclear reactions, it's a tremendous amount of energy which we can harness and we can take advantage of, and we can store and use it to serve mankind. And then for the usual chemical reactions, the rates of reactions are influenced by temperature, pressure, concentration, and catalyst. But nuclear reactions normally they are not affected by these factors. So these are some of the reactions that our radioactive atom can undergo. So um, when it has something to do with the nuclear stability, meaning the radioactive nuclei or an atom that's radioactive, that's unstable. So when it decays, the product of the decay, of course, is a new kind of element, and it can emit some particles, and of course, the radiation or the light energy. And when it decays, the atom become more stable. So one of the common nuclear decay is the beta decay. So in other words, when a nuclei, when an unstable nuclei or radioactive nuclei decays, it gives the electron. So the beta decay, so this refers to electron. So what happens here, the neutron in the nucleus transform into a proton, so giving you an electron plus certain amount of energy. So there is a transformation of a neutron into a proton. So there is a decrease of neutrons by 1, and there's an increase of protons by 1. Just like in these examples, the carbon 14 into nitrogen 14 plus the beta electron, the potassium into calcium. So again, this is a transmutation, meaning a new element is formed. Another common nuclear reaction or decay is the positron. This is just the opposite of your beta electron. It's an electron, but it has a charge of a positive. So it's just like a reverse. So we call this as a positron. So what happens here? The proton is converted into a neutron and emitting the positron, and of course a certain amount of energy. So there will be an increase in the number of neutrons and a decrease in the number of protons. So we have some examples here, our carbon 11 into boron 11 and potassium 38 into argon 38. Again, these are transmutation examples. Another one is electron capture decay. So the unstable atom or nuclei can react with an electron, so giving you a new element and certain level of energy. So just like in our given examples here, argon 37 converted into chlorine 37, and then the iron 55 converted into a manganese. So what happens here? A proton combines with an electron to form a neutron. So basically, the neutron is the mass is slightly higher than a proton. The slight higher in the mass is actually due to is equivalent to the mass of the electron. So we can say that a neutron, it's like it consists of a proton and electron. So proton plus electron gives you a neutron. So there's an increase in the number of neutrons and decrease in the number of protons. Of course, we also have this one, the alpha decay. This is just equivalent to the nucleus of the helium. So, or it could be represented by the symbol alpha. So 4-2. So there's a decrease of neutrons by 2 and decrease in the number of protons by 2. And some radioactive nuclei can undergo spontaneous fission, meaning it breaks apart into smaller and a little more stable nucleus or nuclei than plus neutrons. Like your californium, it gives you indium and then 2 neutrons. And excited nuclei can also give you gamma rays. So this is just a light energy, and there's no transmutation that takes place. So you may ask, why do some nuclei decay? So why do they undergo the nuclear reaction? So it has something to do with the instability of the nucleus, which what I've said earlier. First, the nucleus may be too large, so it's a large molecule, and the strong nuclear force drops when the atoms gets larger, and this nuclear force becomes too weak over the diameter of the nucleus, and what happens, the protons will be pushed apart. And what happens, this large atoms can emit or actually atoms, based on the observation, atoms larger than bismuth, meaning larger than 83, the atomic number, can rapidly emit an alpha particle, or and it becomes a little stable, or they can undergo spontaneous fission. So for too large, so atoms that are too large, so we have alpha particle or spontaneous fission. So when it gives you smaller atoms. Actually, even some nuclei that is not too large can also decay. So when we look at the nuclei that decay, we can discover something. So this nuclei may have numbers of protons and neutrons that are not ideal. This is somewhat similar to the octet rule. So there is some kind of magic numbers for each nucleon that corresponds to certain stability. There are around 264 stable nuclides found in nature, and the given graph here shows the neutron to proton ratio. So neutron to proton ratios of these stable nuclides. So collectively, the nuclides fall within what is known as the band of stability. Okay, so atoms tend to want a certain neutron to proton ratio. So actually, this red line, this corresponds to 1-to-1 neutron to proton ratio, which is outside the band of stability. And there's also around 110, 120, there are also some nuclides under here, so they're considered to be in the island of stability. So they don't, meaning if they are in this region, stability region, so they are not radioactive, or they don't decay. Okay, so when the neutron and then the proton is too large, beta decay can happen. And if too small, when we say when neutron and proton ratio is too large, meaning you have more neutrons, right? So that's why beta decay can happen. So a neutron is converted into a proton and electron. But if it's too small, the positron decay or electron capture can happen. So meaning if it's too small, meaning you have more protons. So it can react with the electron to give you a neutron, or it could emit a positron. And then, as what I've said before, if the atom is in excited state, it can emit a gamma ray. So just like an energy, it's just a light energy. So the gamma ray, like this. So again, if the N to P is too large, the N to P ratio is too large, then beta decay happens. And if it's too small, positron decay or electron capture will happen. Okay, so this is what we call as the magic numbers. So nuclei that are stable have certain numbers of neutrons and protons that are considered extra stable. So if your N or P is equal to 2, 8, 20, 50, 82, 126, similar to the stable numbers for electrons in noble gases. And in addition, nuclei with even numbers of protons and neutrons are more stable than those with odd numbers of neutron and protons. So both even. And then all isotopes with atomic numbers higher than 83, these nuclei are actually radioactive, so they can emit certain level of radiation. Of course, all isotopes of Tc and then Pm, these elements, these are also radioactive. So in summary, so these are the common nuclear reactions. The alpha emission is just equivalent to the helium. The change in protons and the change in the atomic numbers, that's -2. Change in neutrons, -2. Change in mass number, +4. And then the beta is just an electron. So +1 change in proton, -1 change in neutron, and then 0 for the mass number. For the positron, it's just the opposite of the electron. So the change in proton is -1, change in neutron is +1, and then 0 for the change in the mass number. Electron capture, -1 change in proton, and then +1 change in neutron. And then the gamma is no change at all. This is just a light, light energy. So because the different radioactive nuclides have different stabilities, the rates at which they decay differ as well. So these rates are described in terms of a nuclide half-life. So when we say half-life, this is the time it takes for 1/2 of a sample to disappear. And many of the naturally occurring radioactive nuclides have relatively short half-lives. So with such a short half-life, so why are this and other short-lived nuclides still around? So they're still present. So the answer is that although they disappear relatively quickly, so once they form, these nuclides are actually constantly being replenished because they are products of other radioactive decays. Three relatively abundant and long-lived radioactive nuclides are responsible for producing many of the other natural radioactive isotopes on Earth. And one of them is actually the uranium-238, which has this one, uranium-238, which has a half-life of 4.51 billion years, which basically changes to lead here. Okay, from uranium-235 um, in a series of 8 alpha decays and 6 beta decays. We call this sequence of nuclear decay series of this sequence as a nuclear decay series. So because this sequence of decays is happening constantly in soil and in rocks containing uranium, all of the radioactive intermediates between uranium and lead-206, meaning these nuclides and atoms, constantly being formed and are therefore still found in nature. So going back to the half-life, so it's represented by this equation, the number of our, the change in the amount of our radioactive material over the change in time. So we can express that in this equation. This is linear equation. Convert into a linear or algebraic equation. This is y is equal to mx plus b. So these our x is the time, and then our y is the natural logarithm of the n. N0, this is the amount of our material at time 0, and the n is the amount remaining after some time. And the alpha is the decay constant. So the half-life basically is just ln2 over the decay constant, or the decay constant is calculated with the formula ln2 over t1 hat, which is actually derived from this expression. So basically, if you plot the time against the amount at time t, so you get a curve. But when you convert it into a natural logarithm, you get a straight line. So you can actually calculate the amount of the nuclide remaining after some time using this equation. So again, you can plot. Our slope is the decay constant. Slope is the decay constant. It's a negative. That's why our graph is pointing to the left. So our t is our t is our x, and it's the y-intercept, and then our y is the natural logarithm of the amount at time t. So meaning you have a table of the time and then ln n t. So values, 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 and then you can plot it. You can use linear regression, so you can determine the slope and then the intercept. So one of the application of the half-life is of the carbon dating. So we can estimate the age of a certain artifact or any material. The most common is the carbon 14 dating. The carbon 14 has a half-life of 5,730 years. So we can estimate the age of any artifact or any life form, like let's say a bone. So we can determine using the carbon dating. That's one application. So let's go to the very interesting application of this nuclear chemistry. So we have an example here of an unstable uranium which can collide with a neutron, so this one, and produce smaller nuclei and some more neutrons which can collide with more uranium atoms, causing a chain of reaction and the most exciting product, the tremendous amount of energy. So this chain of reaction can be controlled in order to generate electricity, which is actually done in a nuclear power plant. So again, it gives us a tremendous amount of energy. So when you just compare it, so this one is um, to a single uranium. So we generate around 1 mole of not single atom, but 1 mole of uranium-235. It can generate this much of energy, 2.0 times 10 to the 13 joules. That's so big compared to 1 ton of coal in coal power plant. You can only generate, the combustion of that can only generate as much as 5 times 10 to the power 7. So 7, the difference is a million. So it's really a tremendous amount of energy. And that is just for 1 mole. Okay? So we're not talking grams yet. So you convert it into gram. So this is an example. This is what we call as the nuclear fission reaction. So our radioactive can react with small particles like neutron and gives us smaller atoms and more neutrons, which can react we can react further in a chain reaction. Okay, so this is what is being used in nuclear power plant and also in the creation of the nuclear bombs. So the nuclear chain reaction, this is a self-sustaining sequence of nuclear fission reactions. So there is what we call as the minimum amount or mass of our material, fissionable material required to generate a self-sustaining nuclear chain reaction, and we call it as the critical mass. And again, this is the basic principle in the creation of the nuclear bomb. So just like what was the history tells us, no? The Nagasaki and the Hiroshima, so bombarded by the U.S. With this nuclear bomb. And same principle as well, but in a controlled fashion, so we can control the chain of reaction so that it gives us only certain level of energy that we want, like in a nuclear reactor. So we have an activity, I've given you a video, so please go check out the video explaining the explaining how a nuclear power plant works. The video gives you the plant tour inside, and even we have the Bataan nuclear power plant, but it's not functioning after it was built. Okay, but there is now a call of utilizing it, but hopefully because there is a negative notion about nuclear power plant. So we had an activity, also a forum about your stand of this revival of this Bataan nuclear power plant. Some issues about nuclear power plant or nuclear fission is the production of wastes. But if you compare with the coal power plant, so it gives you tons of waste, sulfur dioxide, carbon dioxide, greenhouse gases, and then plus ash. But our nuclear power plant, so no emission of these gases. We just have a vitrified waste, so these are solid, and usually they can be contained and stored underground. Okay. And another emerging technology now, it's very promising in terms of giving us the amount of energy, is the fusion reaction. So whereas nuclear fission reactions yield energy by splitting large nuclei to form much smaller or medium-sized ones. The nuclear fusion reactions release energy by combining small nuclei into larger and some more stable species. So these are the basic reactions that's happening in the sun. So there is this is an emerging field now in energy research. In fact, they have this tokamak magnetic plasma confinement. They study. They try out several small particles. They collide them, and then they determine what the amount of energy that is produced, and the products when these small atoms are um, would collide. So we'll end with this one. So this is a very practical device, the Geiger counter. So this measures the level of radioactivity in a material or in any place. So I would suggest there is a mini series in HBO. I think it's just less than 10 episodes about the account of the Chernobyl power plant. So there was a meltdown, meaning in the nuclear reactor was heavily damaged and causing so many lives and diseases in the people living in the neighboring towns. You can check that out in HBO. Chernobyl. I think Chernobyl was the title. Okay, so that's end our discussion of nuclear chem. I'll be giving also uh, an activity or assignment about this one. So that's it. So I'll see you again in the next topic.